Hi, good afternoon, good morning, good evening, welcome back here. Today we're gonna finish our talk in chapter 9 and move on to chapter 10, which is hypothesis testing dealing with categorical variables. So today we plan on just revisiting comparing two population means from where we left off on last lecture, and then we'll get into overview of analyzing means, or actually dealing with paired samples. And then we're going to jump into chapter 10 and get into the basic ingredients for testing with categorical variables and the chi-square tests for the goodness of fit. So just where we left off last time, we were comparing two population means. And in comparing them, we're looking at, well, are they dependent samples or independent samples? So last time we covered the example with independent samples, and this time we'll deal with dependent samples. But just, as far as dependent goes, we're really looking at paired. Okay, paired samples that are paired together. So maybe it's a before and after comparison, or related to objects such as twin siblings and or spouses. So of course we went over these examples last time and dealing with a, whether to be able to tell whether it's dependent or independent or not with hearing and reading and exercise. And then we got into the hypothesis testing for dealing with two samples here. So really in here, this hypothesis test here, the steps that we see is always the same for hypothesis testing. Okay, it's always hypothesize, prepare, compute to compare, interpret. This never changes no matter what hypotheses or what parameters that we're dealing with here. Okay, but in this table here, of course, we're looking at different null and alternatives for these types of tests. Then of course we did an example here doing this. Okay, so in this example we're just showing you how you crunch these out in StatCrunch. And then of course here is just a nice way if you want to do a two sample t-test with the sample using this where options. You can easily recover the group that you want to test. So here I'm looking at average sleep for students who drink heavily, and then I'm looking at the average sleep for the students that do not drink at all. And so in here, where you start off with the variable name or the column name, in this case is alcohol use, and you type it in exactly as you see it, and then you put an equal sign, and then here I put heavy, and then of course here I put abstain. Okay, so abstain. So it's only going to record the average sleep where the student responded to abstain to the alcohol use. So very, very slick way of doing a two sample test from the raw data using StatCrunch. If we were using like more sophisticated programming, essentially this is what we would be asking the computer to do. Okay, but now we get into paired samples. So we'll want to cover confidence interval for, I call it mu sub d. That's the mean difference. Okay, the mean difference. But really, what we'll find out is that this is just the mean from 9.2 to 9.3. So for these tests here, they're actually the exact same for the one sample hypothesis test for the mean and the one sample confidence interval for the mean. Okay, so it appears to be two sample, but once we take advantage of this dependent design, it just becomes a one sample. Okay, so really everything here is just repeat. Okay, but here we're just talking about the differences. Okay, every time the differences versus individual. So typically we see data that looks like this. Okay, we have student 1, student 2, student 3, student 4, all the way to student 20. And we have the student's first test score, and then we have the student's second test score. Okay, so here we're interested in whether students perform better on the second test rather than the first. So here what we're looking at is, since they are paired, because this is student 1, first and second, so what we do is we look at the difference right away. So all of these represent the difference in each of the test scores. So we did 84 minus 85 here, 88 minus 85 here, 88 minus 78 here, 90 minus 78 here. So we're seeing, at least from the second test score, we're seeing a lot of positive values. Maybe students are doing better on the second test score than the first. Okay, so what we have here, this is our data. Okay, this is our data, which are the differences. And usually we want to test whether these differences are significantly different from 0 or not. Okay, but what this is just one sample t-test. Okay, but we just have to remember that these are not like individual student scores. These are the difference of two scores. Okay, so n here, when we see n, it's not really our sample size per se, because you could do 20 and 20, 40, but it's just the number of pairs, right? Because we're only using this data here. Okay. So so once again, so the confidence interval equation, once again, is just estimator plus or minus a margin of error, right? And once again, we don't know the standard deviation of difference is sigma, so we estimate it with S, right? So my pair T interval is saying, well, this is the sample mean of differences from our data plus and minus the margin of error. So T star is just some multiplier, and how we find it is the same way we did for one sample interval, where we do, you know, degrees of freedom is n minus 1 and 95% level or something like that. And then this SD over root n, this is the sample standard deviation of the differences, right? This is the expected difference between any difference and the average difference, divided by the square root of n, divided by the sample size. So remember, this here, this whole quantity here is the standard error of the sample mean, okay? And this is the multiplier here. So D bar and S are the mean and standard deviation of the sample differences. N is the sample size or number of pairs, and T star tells us how wide the margin of error is in terms of standard errors. Okay, and how we find that is exactly the same. Okay, so if so, here's my data. So I plug in my data here. Here's my first student score, second student score, and what I'm going to do is I'm going to do a pair t-test. Now, just to show you very quickly how that's done. So if I were to open, let's sign in here. So once I open up StatCrunch, I just go here to Stat, and then we go to T-Stat. Okay, so and then there's paired. Okay, once you see paired, well, that's where you plug in. So this is just for the data. So you just say this column is where you find sample 1, this column is where you find sample 2, and this is where you and then you could do interval or hypothesis test. Now, if we're doing a paired t-test and StatCrunch already provides you the sample mean and sample standard deviation of the data, then you just do one sample and do with summary, and then you plug in your sample mean of differences and your sample standard deviation differences and your number of pairs here. Because remember, these tests are the same. Okay, this one sample test and the pair test, they're pretty much the same. The only thing that changes is our interpretation a little bit. Okay, so just a heads up there on how we do that. But anyway, so here we have, so here I'm just saying, here's my data. So my first is here, my second test is here. But remember, I'm doing second minus first. So sample 1 is second score, sample 2 is first score. And then here I want my confidence interval, 95% confidence interval. Okay, so if you do that, you get the output here. So here it's actually telling you the way it took the difference. So let's say it's second score minus first. So actually that matches up to what we originally want to do. So here, this is the sample mean of this is the sample mean of different scores. So we see that definitely it's indication that they're doing better on the second. All right, this average difference is 2.15. So on average, the second test is 2.15% just better. This is our standard error. So remember, how do they find standard error? Well, it's standard deviation of the differences divided by square root of n. So this is 6.05 divided by that, so 1.35. So what that tells you, remember, this is standard deviation, okay, but this is standard deviation of individual differences around the average difference, right? But the standard error, remember, we're using sample mean to estimate the true mean. So this is the expected error we should see between the sample mean and the true mean, the parameter. All right. So so here we have so that's what we get there. So that's the standard error here. Okay. And then degrees of freedom, of course, that's our number of pairs minus 1, 19, number of differences minus 1. And then for here they just give you the lower and upper limit, but remember how they do that. So we could find T star for 95%, degrees of freedom 19. We can use the book if you want to find 2.03. Okay, but from here on out, you're highly encouraged. I mean, you use this reference slide to like check, to help you understand what StatCrunch is giving you. But really, you should be using StatCrunch for all of these calculations. Okay, if you're doing everything by calculator, it's going to take you forever and you're going to make mistakes. Okay, but we want to be precise as possible, so we want to use this technology. So just really understand what this output means. Okay, but anyway, so here I find my T star, which is 2.093. So here I get my sample mean minus the margin of error, where my margin of error is this multiplier times the standard error. So my margin error is 2.03 times the standard error. Okay, so what we get is this negative 0.6837. And then for the upper limit here, sorry, there should be a plus sign there. Okay, for the upper limit here, what we get is we add the margin of error here. Okay, so make sure, I mean, because if you're doing these by hand, you have to be careful how you multiply. Just note that your calculator does not know order of operations. So if you were to plug this in, it's possible I could do the plus sign first, right? But remember, we do parentheses first, then multiply, then add, using PEMDAS. So be careful there if you're doing it by hand. But this kind of relates how they get the output here. But see, in the output, they don't give you this T star, okay? But I show you how to do this in the book, okay? All right, so anyway, so there's our interval, okay? And this is how it relates to the formulas that we presented here, okay? And remember, it's important that we know how to interpret all of these. Okay, so in the end, it says we are 95% confident that the interval negative 0.6837 to 4.9837 contains the true mean difference between second and first exam scores for the students. Okay, so since our interval contains a mean difference of 0, we cannot conclude that exam scores for second exam increased from the first exam. Okay, because remember, we're 95% confident that that our interval contains the mean. So pretty much any value in our interval is a plausible mean value for the mean difference. Okay, and actually this is wrong with it right here. It's not difference of the means, it's just the mean difference. Okay, so since 0 is in our interval, 0 means that no improvement whatsoever. Okay, they're the same. We can't conclude that the second. Okay, because if we look at the sample mean here, we get 2.15, which is indication that it's indication that that there's an improvement on the second test. But what we're saying here is that it's possible that we observe a sample statistic, which we did here. Okay, given that the true mean is 0. Okay, because remember this sampling distribution, right? There's some variation from sample to sample, so it's possible to observe differences very close to 0, such that 0 is still true here. Okay, so if we get into hypothesis test here, well, hypothesis test is going to be the exact same method that we did for one sample hypothesis test for the mean. Okay, so we still follow these exact same 4 steps, and now we state. So here, we state the significance level, state the hypotheses, state any assumptions, and of course here for random sample, independent observations, and of course here large sample. So this is where a slight difference is: the population distribution of differences must be normal, or the sample size, the number of differences, must be large. So in this case, we're not concerned about the differences of test score 1. We're not concerned about the distribution of test score 1 and test score 2. They could be whatever they want, but what we're interested in are the differences. Okay, so we don't make any assumptions on the individual, on the scores from each test. We're only looking at the differences and want to know, okay, well, if sample size is small, then can we assume the differences are normal, or the number of differences is larger than 25? Okay, and of course we have to have big populations. Okay, population at least 10 times larger than the sample size. Okay, but remember, when something like this fails, okay, when this large sample case fails, it just means that our p-value is not accurate and not reliable at all. Okay, so that's what it means. No matter, regardless of the hypothesis test that we're using, if this large sample is not satisfied, whether it's proportion or mean or difference in means or difference in proportion, if this is not satisfied, then our p-value is garbage. Okay, it's not very good at all. Now, if 1 and 2, if random sample and independent observations, and one of these are not satisfied, then what that means is that our data is not good at all. Okay, our data are not good at all. Okay, meaning that we have bias in our data. Okay. So just to look at these compute and compare, well, now our test statistic is the sample difference that we observe, the sample average difference that we observe, and we compare it to the mean difference of the null hypothesis, and we compare this difference to the expected difference we should see between the sample mean and the null hypothesis mean. Okay, so remember, that's what standard error is. It's the standard deviation of the sample mean. And so what this quantity measures here is the typical or average difference we should see between our estimator and the value under the null hypothesis. Okay, so we want to know whether this is significant or not. Okay, so degrees of freedom here are, of course, n-1, and this can be interpreted just like a z-score. It tells you how many standard deviations away the sample mean is from the null hypothesis mean. But we have to be careful for smaller sample size because we are estimating the standard error. For larger sample size, we could be more confident, but definitely if it's smaller, like 5 or 4, we definitely have to be careful how we interpret this. Okay, but anyways, so as far as the hypothesis that we could see, I mean, we have two-sided, one-sided left, one-sided right. These are the exact same ones that we saw in 9.2 and 9.3. So if we revisit this data again, okay, so here we're studying these test scores, first test score, second test score, and we want to know if there's a significant difference or not. And our differences that we're taking is we did second minus the first. So here we are interested to see if the students perform better on the second exam when compared to the first exam. So we want to test this claim using a 5% level of significance. So our alternative hypothesis is that the mean difference in test scores is greater than 0. Okay, that is, exam scores from second exam are better than first exam scores on average. Okay, and of course the null hypothesis is that there's no mean difference in the test scores. Okay, so here we're saying that the mean difference is equal to 0 versus the alternative that the mean difference is greater than 0. Okay, so notice the difference between independent and dependent samples. So for independent, it was difference of the means, mu1 minus mu2, right? But when they're dependent, it's first we take the differences and then we take the average, right? Whereas when it's independent, first we take the averages and then we take the difference of the averages. Okay. So if I were to test this out, I do the same test that I would use for the previous tests, right? And what I would get here is I could do the paired test following the same steps that we did before in StatCrunch. And here we would get our mean, our standard error, our degrees of freedom, and now our t statistic and our p-value. Okay, so of course the sample mean, we saw the same one for the confidence interval. This is the sample mean of differences, and this is my standard error, right? This is the expected difference we should see between the sample mean and the null hypothesis mean difference of 0. Right, and our degrees of freedom, that's our sample size minus 1, and then of course we get our t-test statistic here. Okay, what this is saying roughly that my sample mean is 1.58 standard deviations greater than the null hypothesis mean. Okay, and then my p-value here is roughly 6.44%. Okay, so of course I introduced this slide here. Okay, and these slides are also on Canvas, but here I'm just kind of mapping these numbers to the formulas that have been presented here. Okay, so here we see our t-test statistic, we sample mean minus mean under null divided by standard error, right? And that's what we get here, and that's the number that we get here for our test statistic. Right? And for our p-value, use technology. Okay, so your book may attempt to approximate p-values using the book, and don't ever do that because they're very inaccurate. Given something like StatCrunch or just technology in general, we can find the p-value. Okay, but in general, the t-table is not very good in finding probabilities. All right, so if I go in here, I find the p-value. So since it's a greater than alternative, it's the p-value. It's assuming there is no difference. Assuming there is no difference in student performance on each exam, there is a 6.44% chance of observing an average difference of 2.15 points or larger. Right, now the reason it's larger is just because it's a one-sided test, right, with a greater than alternative. Right, so my p-value represents that, observing 1.58, observing a sample mean or larger, right? And so really, this here, we're talking about a sample mean here, but of course this is our test statistic, so they're the same. Okay, so this is 1.58 or larger. So this shaded region represents the p-value. Now, is this a surprise? Is this a surprise? Well, it depends on what alpha is. Right, it depends on what alpha is. So actually this is I tested at 5%. Okay, so here we're saying since 0.0644 is larger than 0.05, we failed to reject the null hypothesis H0. and therefore we conclude that at a 5% significance level, there is not enough evidence to conclude that the scores from the second test are significantly larger than the scores from the first test on average. Okay, so I mean, the remainder of chapter 9 is just dealing with the two sample test, and what we have there is that, well, either we have dependent samples or independent samples. And what we learned today is that if they're dependent samples, the process for calculating intervals and hypothesis tests for the mean difference is the exact same stuff that we did before in the previous chapters of 9, with just one sample t-test and confidence interval. So no difference there, nothing new there. It's just our interpretations are slightly different in the fact that we're mentioning the difference. Right? Whereas the independent samples, well, that takes a little bit more work to calculate there, and we learned some new notation in that type of test. Okay, but that's all we have for today. Next time we'll jump into chapter 10.